300 miles off the Oregon coast, a volcano is counting down. Scientists say it will erupt in 2026. But this is not just about one underwater mountain. This is about what happens when the Earth reminds us who is really in charge. Chapter 1: The Breathing Mountain. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. 300 miles off the coast of Oregon, something ancient is stirring. A mile beneath the Pacific Ocean, in waters so dark that sunlight has never touched the seafloor, a mountain is breathing. Not breathing like you and me, breathing like a planet, rising, swelling, building pressure that has been accumulating for nearly a decade. The instruments say it will happen soon. The scientists say 2026. And when it does, we will witness something extraordinary, something terrifying, something that forces us to remember just how small we are on this spinning ball of rock and fire. This is the story of Axial Seamount, the most monitored underwater volcano on Earth, a ticking clock counting down beneath the waves while most of the world sleeps unaware, a geological time bomb that connects to a much larger and far more dangerous system, one that has already reshaped human history, one that could do it again. But before we dive into the darkness, we need to understand what we are dealing with. We need to understand why scientists are watching this particular volcano with such intense fascination. And we need to understand what a volcanic eruption can truly do when it decides to remind humanity who is really in charge of this planet. The Pacific Northwest of America projects a certain image. Forests thick with Douglas fir and western red cedar, rivers fat with salmon, cities known for coffee and technology and a particular kind of creative energy: Seattle, Portland, Vancouver. Millions of people going about their daily lives, checking their phones, worrying about traffic, planning their weekends. They do not think much about what lies beneath their feet. They do not think about the ancient forces grinding away in the darkness below. But scientists do. And what they have discovered should make everyone in the region pay very close attention. The ocean floor off the Oregon coast is not stable ground. It never has been. For 200 million years, the Earth has been engaged in a slow-motion collision in this region. The Juan de Fuca plate, a slab of oceanic crust roughly the size of Montana, is sliding beneath the North American continent at a rate of about 4 centimeters per year. That may sound insignificant, the width of your thumb. But over geological time, this relentless movement has built mountains, created volcanoes, and generated some of the most powerful earthquakes this planet has ever experienced. Right in the middle of this chaos sits Axial Seamount. Picture a mountain rising from the ocean floor, not just any mountain, a shield volcano built from countless eruptions over hundreds of thousands of years. Its base spreads across the seafloor like a great rounded dome. Its summit reaches upward through 3,600 feet of water to within 1,400 meters of the surface, still deep enough that no ship would ever notice it passing overhead, deep enough that the crushing pressure would kill any unprotected human in seconds, but not deep enough to contain the forces building within. Axial Seamount sits at a geological crossroads that makes it uniquely active. It perches directly on the Juan de Fuca Ridge, the spreading center where new oceanic crust is being created as tectonic plates pull apart at a rate of 6 centimeters per year. But that is only half the story. Axial also sits atop a hotspot, a plume of superheated rock rising from deep within the Earth's mantle. The combination of spreading ridge and hotspot creates something extraordinary. A volcano with an unusually robust magma supply. A volcano that erupts more frequently than almost any other in the northeastern Pacific. A volcano that scientists can actually study in real time. The summit of Axial features something remarkable: a caldera. Not a cone like Mount St. Helens or Mount Fuji. A caldera is a depression, a giant bowl formed when a volcanic eruption drains the magma chamber below and the ground collapses into the void left behind. Axial's caldera measures roughly 3 kilometers by 8 kilometers, rectangular in shape, an unusual geometry that hints at the complex forces at work beneath. Inside this caldera, and along the rift zones extending to the northeast and southwest, the seafloor is a landscape of frozen chaos. Lava flows twist and ripple across the terrain, some smooth and ropey, some broken into jagged blocks. Hydrothermal vents belch superheated water, At temperatures exceeding 700 degrees Fahrenheit, black smokers tower above the seafloor, mineral chimneys, built by chemical reactions between volcanic fluids and cold seawater. The chimneys host entire ecosystems. Giant tube worms cluster around the vents. Ghostly white crabs pick through the debris. Microbes thrive in conditions that would kill almost anything else on Earth. Life clinging to the edge of destruction. Axial erupted in 1998. It erupted again in 2011, and again in 2015. Each time, the pattern was similar. The seafloor swelled as magma accumulated in the shallow chamber beneath the caldera. Earthquake activity increased, and then suddenly the volcano let go. Lava burst from fissures along the caldera floor and rift zones. The seafloor dropped as the magma chamber emptied. In 2015, the caldera floor fell by more than 2 meters in a matter of hours. After each eruption, the cycle began again. Inflation, swelling, building pressure, the seafloor rising centimetre by centimetre as fresh magma flowed into the chamber from below. Scientists watching, measuring, waiting. What makes Axial Seamount remarkable is not just its activity, it is how closely we can observe that activity. In 2014, Axial became part of the Ocean Observatories Initiative, a network of underwater instruments connected to shore by fibre optic cables. For the first time in history, scientists could monitor an active submarine volcano in real time. Seismometers recorded every earthquake, every tremor, every subtle shift in the crust. Pressure sensors measured the inflation of the seafloor with millimeter precision. Temperature probes tracked the heat flowing from hydrothermal vents. Cameras captured images of the alien landscape below. When Axial erupted in April 2015, scientists were watching. They had actually predicted the eruption months in advance based on the inflation patterns they observed. It was a triumph for volcano science. The first successful forecast of a submarine volcanic eruption, a proof of concept that opened new possibilities for understanding these hidden giants. Now those same scientists are watching again, and what they see concerns them. Since 2015, Axial has been inflating steadily. The seafloor has risen. The magma chamber has been refilling. Earthquake activity has fluctuated, but the overall trend points toward one inevitable conclusion. Another eruption is coming. The current forecast places the next eruption somewhere in mid to late 2026. Scientists have repeatedly adjusted their predictions as conditions changed. First they thought 2024, then 2025. The volcano has been teasing them. Inflation rates speed up and slow down in ways that are difficult to predict. But the fundamental physics remain clear. Magma is accumulating. Pressure is building. Eventually something will give. When Axial erupts, the immediate effects will be contained. This is important to understand. The volcano sits 300 miles offshore and nearly a mile underwater. The eruption style is effusive, not explosive. Think of Kilauea in Hawaii, not Mount St. Helens. Lava will flow across the seafloor, the caldera will collapse, hydrothermal activity will intensify, but no massive explosion will send ash into the atmosphere. No pyroclastic flows will race across populated areas. No direct threat to human life exists from this particular eruption. So why should we care? Because Axial Seamount is part of something much larger, something that connects to the entire volcanic and seismic system of the Pacific Northwest, something that reminds us of the terrifying power that lies dormant beneath our feet. And because studying Axial teaches us about volcanic processes that can devastate civilizations when they occur on land, 300 miles may seem like a comfortable buffer, but it is not the eruption itself that should concern us. It is what the eruption represents. It is the reminder that the Juan de Fuca plate is active and in motion. It is the connection between seafloor volcanism and the much more dangerous Cascadia subduction zone. It is the historical record showing that volcanic activity in this region has repeatedly coincided with massive earthquakes. The Pacific Northwest is overdue. Scientists estimate a 37% chance of a magnitude 8 or greater earthquake on the Cascadia subduction zone within the next 50 years. A 10 to 15% chance of a magnitude 9 event that would rupture the entire fault from Northern California to British Columbia. An earthquake that would make the 2011 Japan disaster look modest by comparison. Axial Seamount will not cause that earthquake, but it is part of the same system. It is a symptom of the same underlying forces, and studying it helps us understand what we are truly dealing with. The breathing mountain beneath the waves is sending us a message. The question is whether we are listening. In the chapters ahead, we will dive deeper into this story. We will explore how scientists predict volcanic eruptions and why it remains so difficult despite our advanced technology. We will examine what happens when volcanoes go catastrophically wrong. We will look at the historical record of volcanic disasters that reshaped human civilization. We will connect Axial to the larger story of the Cascadia subduction zone and the earthquake that is coming whether we like it or not. And we will ask the question that haunts every scientist who studies these systems. What happens when the next big one arrives and finds us unprepared? The breathing mountain is patient. It has been building toward this moment for years. It will continue building until the pressure becomes too great to contain. And then, in the darkness beneath the Pacific, fire will meet water once again. The countdown to 2026 has begun, but this is more than just one volcano off the coast of Oregon. This is a window into the violent heart of our planet. A reminder that the ground we walk on is a thin skin stretched over forces we barely understand. Forces that have shaped the course of human evolution. Forces that have ended civilizations. Forces that continue operating in the darkness, whether we acknowledge them or not. Axial Seamount is currently inflating at a rate that suggests eruption thresholds will be reached sometime in the coming year. Scientists track the expansion through networks of pressure sensors anchored to the seafloor. They measure tiny earthquakes that indicate magma movement. They watch the data stream in real time through cables running to a shore station in Pacific City, Oregon. The technology is remarkable. A decade ago, monitoring a submarine volcano in this detail would have been impossible. Now scientists can watch Axial breathe from the comfort of their offices. They can see the mountain swell. They can detect the earthquakes that signal stress accumulating in the rock. They can even live stream footage from cameras positioned on the seafloor. But technology has limits. Predicting exactly when a volcano will erupt remains one of the great challenges in Earth science. Volcanoes do not follow schedules. They do not issue press releases. They do what they want when they want, according to physical laws we still do not fully understand. The scientists studying Axial have already been wrong multiple times. They predicted eruption by the end of 2024. It did not happen. They pushed the forecast to 2025. Still waiting. Now they say mid to late 2026. Maybe, probably, if current trends continue, if inflation rates remain steady, if the earthquakes pick up as expected. That uncertainty is not a failure of science. It is an honest acknowledgement of how complex these systems truly are. Volcanic eruptions depend on countless variables: magma viscosity, gas content, rock strength, stress accumulation, temperature gradients, pressure dynamics. Any one of these factors can change the timeline in ways that models cannot predict. What the scientists can say with confidence is this: the eruption is coming, maybe in 6 months, maybe in 18 months, maybe sooner. The volcano has shown us its pattern 3 times now, and there is no reason to believe the pattern will break. Axial will erupt again because that is what Axial does. That is what it has been doing for hundreds of thousands of years, and when it does, we will learn something new about how volcanoes work. We will refine our models, improve our predictions, get a little better at reading the signs. That knowledge matters because the same processes operating beneath Axial operate beneath volcanoes all over the world, including volcanoes that can kill millions of people if they decide to wake up. This is the value of studying Axial Seamount. It is a natural laboratory, a place where we can watch volcanic processes unfold in real time without risking human life. Every eruption teaches us something. Every observation adds to our understanding, and that understanding may someday save lives when a volcano threatens a populated area and we need to know whether to evacuate. The breathing mountain does not care about our schedules or our scientific ambitions. It operates on its own timeline, driven by forces that began long before humans existed and will continue long after we are gone. But we are watching now. We are paying attention, and that makes all the difference. In the next chapter, we will go deeper into how scientists study this volcano and what they have learned from years of continuous observation. We will meet the instruments that monitor Axial around the clock. We will understand the physics of volcanic inflation and the delicate art of eruption forecasting. And we'll see why predicting volcanic eruptions remains one of the hardest problems in all of Earth science. The breathing mountain awaits, the countdown continues, and somewhere in the darkness beneath the Pacific, magma rises toward the surface, building pressure that must eventually be released. 2026 is coming. The question is not if Axial will erupt. The question is what it will teach us when it does. Chapter 2: A laboratory beneath the waves. The greatest scientific discoveries often come from the most inhospitable places: the vacuum of space, the frozen depths of Antarctica, the crushing darkness of the deep ocean. These environments strip away the comfortable illusions we construct about our control over nature. They remind us that the universe does not care about human convenience. And sometimes, that indifference creates opportunities for understanding that would be impossible anywhere else. Axial Seamount is such a place. Picture what it takes to study a volcano sitting beneath a mile of seawater. No human can survive unprotected at that depth. The pressure would crush a submarine not specifically engineered. For deep ocean operations, darkness is absolute below a few hundred meters. The currents are unpredictable. The terrain is treacherous. Volcanic activity can change the landscape without warning, burying instruments under fresh lava flows or destroying expensive equipment in moments. For decades, scientists studying submarine volcanoes had to rely on occasional visits, ship expeditions lasting a few weeks at a time, submersible dives measured in hours, snapshots rather than continuous observation, like trying to understand a forest by looking at photographs taken years apart. Everything changed in 2014 when Axial Seamount became part of the Ocean Observatories Initiative regional cabled array. The concept was audacious: run nearly 900 kilometers of fiber optic cable from shore out to the Juan de Fuca Ridge, establish permanent monitoring stations on the seafloor, connect instruments to a power grid that could keep them running continuously, stream data back to scientists in real time. The cable itself is a marvel of engineering. It carries both power and data across hundreds of miles of open ocean and complex seafloor terrain. At various points along its length, primary nodes provide power and connections. Secondary nodes distribute that power and connectivity to individual instruments. The entire system is designed to operate for decades with minimal human intervention. At Axial Seamount, the cabled array includes an extraordinary suite of instruments. Seismometers listen for earthquakes, recording every tremor no matter how small. Bottom pressure recorders measure changes in the height of the seafloor with millimeter accuracy. These instruments can detect inflation as magma accumulates in the chamber below. Tiltmeters track subtle changes in the angle of the seafloor that might indicate magma movement. Temperature sensors monitor hydrothermal vents. Chemical sensors analyze the composition of vent fluids. And cameras capture images of this alien landscape 24 hours a day. The data streams in continuously. Scientists at the University of Washington in Seattle receive real-time information about what is happening on the seafloor 300 miles offshore. They can track the buildup of pressure in the magma chamber. They can watch earthquakes cluster in particular areas. They can see patterns emerging over months and years that would have been invisible with occasional visits. This is the first time in history that a submarine volcano has been monitored so comprehensively, and the results have been remarkable. Consider what scientists learned from the 2015 eruption. In the months leading up to the event, the seafloor at Axial was inflating at a rate that suggested magma was accumulating rapidly. Earthquake activity increased as rock fractured under growing stress. The inflation rate and seismic activity followed patterns that scientists recognized from the 1998 and 2011 eruptions. Based on these observations, researchers made a prediction. Axial would erupt by the end of 2015. They were right. On April 24, 2015, a swarm of earthquakes signaled the beginning of the eruption. Within hours, lava was flowing from fissures along the caldera floor. The seafloor that had been inflating for years suddenly dropped more than 2 meters as magma drained from the chamber. Fresh black basalt spread across the terrain, burying previous lava flows and whatever instruments happened to be in the path. The cabled array captured the entire event. Seismometers recorded thousands of earthquakes in the first day alone. Pressure sensors documented the exact moment when the caldera began to collapse. Temperature sensors detected the thermal pulse from fresh lava entering the water. It was the most detailed observation of a submarine volcanic eruption ever recorded. scientists discovered things they had never known before. The eruption progressed along the rift zones in a particular sequence. The earthquakes migrated in patterns that revealed how magma was moving through the crust. The relationship between inflation, seismicity, and eruption followed a repeatable pattern that suggested future eruptions might be predictable. This last discovery was crucial. If Axial follows a consistent pattern, then scientists should be able to forecast eruptions based on observable precursors. Not perfectly, not with certainty, but with enough accuracy to be useful. The concept they developed is called inflation predictability. The idea is simple in principle. Each eruption at Axial appears to be triggered when the volcano reaches a certain level of inflation. When the magma chamber fills to a particular threshold, the pressure becomes too great for the overlying rock to contain. The volcano erupts. The chamber empties. The cycle begins again. If true, then predicting the next eruption becomes a matter of tracking, inflation and extrapolating when the threshold will be reached. But nothing in volcano science is ever that simple. The inflation rate is not constant. Sometimes the volcano swells quickly, sometimes slowly, sometimes the rate changes unexpectedly with no obvious explanation. The threshold itself may vary between eruptions. The 2015 eruption occurred at a slightly higher inflation level than the 2011 eruption, which occurred at a higher level than 1998. Is this a trend that will continue, or is it random variation? Earthquake activity adds another layer of complexity. Eruptions at Axial appear to require both sufficient inflation and sufficient seismic activity. The magma chamber needs to be full, but the rock also needs to be stressed enough to fracture and allow magma to escape. Sometimes inflation proceeds without much seismicity. Sometimes earthquakes cluster without triggering eruption. Predicting when both conditions will align is extraordinarily difficult. Scientists have repeatedly adjusted their forecasts for the next eruption. They initially expected it by the end of 2024 based on inflation trends observed in 2023. But the inflation rate slowed. Seismicity remained low. The forecast shifted to 2025, then to mid or late 2026. Each revision represents new information. Each adjustment reflects a better understanding of how the volcano actually behaves, rather than how scientists expected it to behave. This is not failure. This is science working as it should. Hypotheses tested against data, models refined as observations accumulate, predictions updated as understanding improves. The current forecast suggests that Axial will reach the inflation threshold from the 2015 eruption sometime in 2026. But researchers have added another criterion. They now believe that eruptions require not just a certain level of inflation, but also a certain level of seismic activity. Based on past patterns, they estimate that 500 earthquakes per day represents a threshold that must be exceeded before eruption becomes likely. As of late 2025, Axial is showing steady inflation but relatively low seismicity. Most days see around 100 earthquakes rather than 500. The volcano is swelling, but not yet showing the stress signals that preceded previous eruptions. This does not mean the volcano will not erupt. It means that predicting exactly when remains uncertain. The inflation could accelerate, seismicity could spike suddenly, or the volcano could continue building pressure for months longer than expected. The uncertainty is frustrating but honest. Scientists have recently launched a new experiment designed to push eruption forecasting even further. A team from Uppsala University in Sweden and ETH Zurich in Switzerland has developed a physics-based model for predicting failure events in geological systems. They have applied this model to landslides, rock bursts, and volcanic eruptions with some success in retrospective analysis. Now they are testing the model on Axial Seamount in real time. Each month, the team generates a forecast based on the latest data from the cabled array. They encrypt the forecast with a timestamp and archive it publicly. The forecast is not released until after the eruption occurs. This prevents any possibility of adjusting predictions after the fact. The experiment is designed to test whether physics-based modeling can outperform simple pattern recognition. If successful, it could revolutionize volcano forecasting worldwide. If unsuccessful, it will still provide valuable information about the limits of current approaches. The stakes are higher than one submarine volcano off Oregon. The same methods developed at Axial could potentially be applied to dangerous volcanoes near populated areas. Every improvement in forecasting could save lives. But there is a shadow over all of this work. The Ocean Observatories Initiative that makes these observations possible faces an uncertain future. The program is funded by the National Science Foundation. Budget proposals have suggested cutting that funding by as much as 80%. If those cuts occur, the cabled array at Axial could go dark. Scientists have secured funding to keep the array operational through the summer of 2026. Beyond that, nothing is guaranteed. The possibility exists that after years of continuous observation, after developing unprecedented understanding of how this volcano works, after correctly forecasting the 2015 eruption, the scientific community could lose access to Axial Seamount just as it approaches its next eruption. This would be a tragedy for volcano science. Axial represents an irreplaceable opportunity. No other submarine volcano has been monitored so comprehensively. No other location offers such detailed, real, time data on magmatic processes. Losing access now on the threshold of another predicted eruption would set the field back by years, if not decades. The scientists working on Axial are acutely aware of this uncertainty. They continue their research knowing that their instruments could go silent at any time. They publish findings as quickly as possible, ensuring that whatever happens to the program, the knowledge gained will not be lost. There is something poignant about this situation. Humanity has developed the technology to monitor a volcano from the other side of an ocean. We can track inflation with millimeter precision. We can detect earthquakes too small for any human to feel. We can watch magma moving through the crust in real time. And yet we may choose to turn off those instruments because we cannot agree to fund them. The volcano does not care about our budget debates. It will erupt whether we are watching or not. The question is whether we will be there to learn from it. For now, the instruments continue operating. Data streams in 24 hours a day. Scientists analyze patterns and refine predictions. The cabled array remains one of the most sophisticated volcano monitoring systems ever built. And somewhere beneath the Pacific, Axial Seamount continues breathing, swelling, building toward the moment when pressure exceeds strength and fire meets water once again. The laboratory beneath the waves is open for business. The experiment continues. The next eruption draws closer with each passing day, and the scientists watching from shore hope they will still have eyes on the volcano when it finally decides to let go. What they learn could change how we understand volcanic hazards worldwide. What they learn could save lives in places far from the Oregon coast. What they learn could advance humanity's ability to predict one of nature's most destructive forces. But only if we keep watching. The cabled array at Axial Seamount represents the best of what science can achieve. International collaboration, advanced technology, patient observation over years and decades, the willingness to ask hard questions and accept uncertain answers. It also represents the fragility of scientific enterprise, the dependence on political decisions made far from the laboratory, the vulnerability to budget cuts that prioritize short-term savings over long-term knowledge, the reality that even the most important research can be abandoned if funding disappears. The breathing mountain beneath the waves does not understand any of this. It follows laws older than humanity and more fundamental than any political system. It will continue building pressure regardless of what happens in congressional hearing rooms. It will erupt on its own schedule, driven by forces that care nothing for human affairs. The only question is whether we will be paying attention when it does. In the next chapter, we will explore the science of eruption prediction in more detail. We will understand why forecasting remains so difficult despite advanced technology. We will see what scientists can and cannot tell us about when a volcano will erupt. And we will confront the uncomfortable truth that even our best predictions come with significant uncertainty. The volcano waits for no one, the countdown continues, and the laboratory beneath the waves keeps generating data that could change everything we know about how Earth works, if we are willing to listen. Chapter 3. The Science of Prediction. Predicting the future is humanity's oldest obsession. We have always wanted to know what comes next. When will the rains arrive? When will the harvest fail? When will our enemies attack? For most of history, we turned to priests and prophets, reading meaning into animal entrails and star positions. We imagined that the universe was sending us coded messages that the right person could interpret. Modern science offers something different. Not prophecy, but probability. Not certainty, but informed estimates based on observable patterns. The scientific method allows us to make predictions that are not just wishful thinking or educated guesses, but testable hypotheses grounded in physical law. Volcano forecasting sits at the frontier of this enterprise. It represents one of the hardest prediction problems in Earth science, and understanding why reveals something fundamental about the nature of complex systems and the limits of human knowledge. A volcano is not a simple machine with easily measurable inputs and predictable outputs. It is a chaotic system where small changes in initial conditions can produce dramatically different outcomes. The rock through which magma rises is not uniform. It varies in strength, porosity, and fracture density from meter to meter. The magma itself changes composition as it rises, releasing dissolved gases and crystallizing different minerals at different depths. Underground chambers connected by hidden pathways create plumbing systems that are invisible to surface observation. To predict when a volcano will erupt, scientists would ideally need to know the exact geometry of the magma system, the precise stress state of the surrounding rock, the composition and temperature of the magma at every depth, and the rate at which new magma is being supplied from below. They would need to understand how all these factors interact and how small perturbations might cascade through the system. They have none of this information, not for any volcano on Earth. The deep structure of volcanic systems remains largely hidden. Scientists work with indirect evidence, inferring what they cannot see from what they can measure at the surface. This is why volcanic forecasting relies heavily on pattern recognition. If a volcano follows a consistent sequence of precursors before each eruption, then observing those precursors again suggests another eruption may be coming. The approach is empirical rather than predictive in a physics sense. Scientists identify correlations between observable signals and subsequent eruptions, then watch for those signals to repeat. Axial Seamount is unusually well suited for this approach. It has erupted 3 times in the past 3 decades under scientific observation. Each eruption followed a similar pattern: years of inflation as magma accumulated, increasing earthquake activity as stress built in the crust, then eruption when certain thresholds were exceeded. The pattern seems repeatable. The volcano appears to be inflation predictable. Scientists can track the inflation in real time and extrapolate when the threshold might be reached. But pattern recognition has serious limitations. First, the pattern might change. Volcanoes are not obligated to repeat themselves. The conditions that produce past eruptions might not apply to future ones. The threshold could shift. The triggering mechanism could vary. Scientists cannot know whether the pattern will hold until the next eruption actually occurs. Second, extrapolation involves assumptions that may be wrong. Scientists project future inflation based on current rates, but rates change. The volcano might accelerate, it might slow down, it might pause entirely for reasons that are not apparent in the data. Every forecast is conditional on assumptions about future behavior that cannot be verified in advance. Third, eruption is not determined solely by inflation. Other factors matter: gas pressure in the magma, strength of the chamber walls, stress conditions along potential pathways to the surface. Any of these could trigger or delay an eruption in ways that inflation measurements alone cannot predict. Consider what happened with the current forecast for Axial. In 2023, the inflation rate looked like it would bring the volcano to eruption threshold by late 2024. Scientists issued a forecast window extending through 2025. The volcano kept inflating but did not erupt. The inflation rate slowed. Seismicity remained lower than expected. The forecast had to be revised. This is not a failure of the scientists or their methods. It is an honest confrontation with uncertainty. The forecast was reasonable given the data available at the time, but the volcano did not cooperate. New data required new analysis and revised predictions. The same thing has happened repeatedly in the history of volcanic forecasting worldwide. Mount St. Helens in 1980 provided one of the most famous examples. Scientists monitoring the volcano saw clear signs of impending eruption. The mountain was bulging outward as magma accumulated. Earthquakes were increasing, steam vents were opening, all the classic precursors were present, but the timing and nature of the eruption remained uncertain. The volcano could blow at any moment, or it might stabilize. The mountain could produce a vertical eruption or a lateral blast. Scientists issued warnings but could not specify exactly when or how the volcano would release its energy. When the eruption finally came on May 18th, 1980. It was more violent and more asymmetrical than many expected. A massive landslide triggered a lateral blast that devastated hundreds of square miles. 57 people died, including several who were in areas considered relatively safe based on the best available predictions. The Mount St. Helens experience crystallized a hard truth about volcanic forecasting. Even when scientists can confidently say that an eruption is coming, they often cannot say exactly when it will occur or precisely what form it will take. The uncertainty is not a result of inadequate technology or lazy science. It reflects genuine complexity in volcanic systems that resist simple prediction. Since Mount St. Helens, volcanic forecasting has improved significantly. Better instruments, more data, sophisticated computer models, pattern, recognition refined through decades of study. Scientists can now provide more accurate warnings with longer lead times than was possible in 1980. But the fundamental challenge remains. Volcanoes are complex systems operating according to principles we do not fully understand, with crucial information hidden deep underground where we cannot observe it directly. Every forecast involves uncertainty. Every prediction comes with caveats. At Axial Seamount, scientists are pushing the boundaries of what is possible. The comprehensive monitoring from the cabled array provides data that would have been unimaginable a generation ago. The repeated eruptions have established patterns that inform predictions. The remote location means that forecast uncertainty does not risk human lives. This is why Axial is such a valuable laboratory. It allows scientists to test forecasting methods under real-world conditions. If the predictions prove accurate, the methods can be refined and applied. Elsewhere, if the predictions fail, the failures provide information that improves future attempts. The new physics-based forecasting experiment represents an attempt to move beyond pure pattern recognition. Instead of simply watching for precursors that preceded past eruptions, the researchers are trying to model the physical processes that lead to failure. They're asking not just what patterns preceded eruptions, but why those patterns occur and how they relate to the underlying physics. The approach draws on research into catastrophic failure in other systems. Landslides, rock bursts in mines, glacier collapses, each involves materials under stress that eventually fail when certain conditions are met. The researchers have developed mathematical models that describe how failure approaches and how observable signals change as the failure point nears. Applied to Axial, the model takes inflation and seismicity data and attempts to identify signatures of approaching failure. If the volcano is following a predictable path toward eruption, the model should be able to detect that path and estimate when eruption will occur. The experiment is ongoing. Monthly forecasts are generated and archived. The results will not be released until after the next eruption allows evaluation of how well the model performed. If successful, the physics-based approach could represent a significant advance over pattern recognition alone. It might allow forecasting at volcanoes where limited historical data makes pattern recognition difficult. It might provide better uncertainty estimates. It might identify early warning signs that pure empiricism would miss. But physics-based models have their own limitations. They require assumptions about parameters that cannot be measured directly. They simplify complex systems into tractable mathematical forms. They can be wrong in ways that are not immediately apparent. The honest answer is that no one knows how well the new approach will work until it is tested against reality. The next eruption at Axial will provide that test. Until then, scientists can only hypothesize and hope. This is the nature of volcanic forecasting in 2026, better than it has ever been. Still profoundly uncertain, improving steadily through hard work and honest evaluation of methods, but facing fundamental limits imposed by the complexity of natural systems and our inability to observe crucial processes directly. The public often wants binary answers. Will the volcano erupt or not? When exactly will it happen? Is my family safe? Scientists cannot provide that certainty, and it would be dishonest to pretend otherwise. What scientists can provide is probability. There is a high probability that Axial will erupt within the next 1 to 2 years based on current trends. The exact timing cannot be specified. The uncertainty reflects real unknowns in the system, rather than inadequate science. For Axial Seamount, this uncertainty has no practical consequences. No one lives on the volcano. No infrastructure is threatened. The only cost of a wrong forecast is scientific embarrassment, which is unpleasant, but not dangerous. For volcanoes near populated areas, the stakes are much higher. A false alarm can trigger expensive evacuations, economic disruption, and loss of public trust. A missed warning can cost lives. Scientists face pressure to be both cautious and decisive, to warn without crying wolf, to protect the public without triggering unnecessary panic. These tensions have no easy resolution. They are built into the problem of forecasting complex systems. Every volcano scientist struggles with them. Axial Seamount provides a space where the struggle can occur without immediate human consequences. Lessons learned here can inform forecasting everywhere. Methods refined at Axial can be applied to dangerous volcanoes worldwide. The breathing mountain beneath the Pacific is teaching us something important. It is showing us the limits of prediction, while also demonstrating how far we have come. It is testing our methods against reality in ways that few other volcanoes allow. And when it finally erupts, whether in 2026 or 2027, or some other year that models fail to predict, the data will show us where we went right and where we went wrong. That feedback is precious. It is how science advances. It is how we get better at understanding the forces that shape our planet. The countdown continues. The predictions remain uncertain. The volcano keeps building pressure according to its own inscrutable logic. Somewhere beneath the Pacific, magma rises through fractures in ancient rock. Gases dissolved under tremendous pressure seek pathways to lower pressures above. Crystals form and settle. The system evolves moment by moment in ways we cannot fully track. All we can do is watch, measure, model, predict as best we can, and wait. The next eruption will test everything we think we know. It will reveal whether our patterns hold or break. It will show whether physics-based models outperform empiricism. It will advance volcanic science in ways we cannot anticipate until it happens. That is the nature of science. Hypotheses tested against reality. Knowledge built from observation rather than assumption. Understanding earned through patience and humility. The volcano waits for no one. The predictions remain provisional. And the scientists watching from shore know that whatever happens next will teach them something they did not know before. That is enough. That is science. That is how we learn. In the next chapter, we will shift focus from prediction to consequence. We will examine what happens when volcanic eruptions go catastrophically wrong. We will explore the mechanisms by which volcanoes can devastate populations and reshape civilizations. And we will see why even a relatively small underwater eruption like Axial deserves our attention, because the forces at work beneath Axial Seamount are the same forces that have caused mass extinctions and near-human extinction in the past. The scale differs, the principles do not. Understanding those principles may be the most important thing volcanologists can teach us, not just for protecting ourselves from the next eruption, but for understanding our place on a planet that operates on timescales and with powers that dwarf anything in human experience. The volcano is patient, the volcano is powerful, and the volcano has lessons to teach anyone willing to listen. Chapter 4. The Anatomy of Catastrophe. Axial Seamount will erupt. Scientists agree on that much. The timing remains uncertain, but the outcome is not. Magma will break through the seafloor. Lava will flow, the caldera will collapse, and then the cycle will begin again. For most of us watching from shore, this eruption will be an abstraction. A scientific event occurring far offshore in darkness so deep that light has never touched it. We will read headlines and move on with our lives. But the processes at work beneath Axial Seamount are the same processes that have ended civilizations, the same forces that turned prosperous regions into wastelands, the same mechanisms that have pushed human populations to the brink of extinction. To understand why volcanic eruptions matter, we need to understand what they can do when conditions align to produce catastrophe. Start with the basics. A volcanic eruption is the release of material from beneath the Earth's surface. Molten rock called magma rises through the crust, driven by buoyancy and gas pressure. When it reaches the surface, it becomes lava. The eruption continues until the driving pressure is exhausted or the pathway to the surface is blocked. This simple description covers an enormous range of events. Some eruptions produce gentle lava flows that tourists photograph from safe distances. Others generate explosions that can be heard thousands of miles away. The difference lies in details that determine whether magma reaches the surface quietly or violently. The most important factor is viscosity. How easily does the magma flow? Low viscosity magma like basalt is runny. Gases can escape easily as it rises. When it reaches the surface, it tends to flow outward in rivers of molten rock. Dangerous certainly, but predictable. Slow enough to escape. This is what happens at Axial Seamount and at most ocean ridge volcanoes. High viscosity magma like rhyolite is sticky. Gases cannot escape easily. Pressure builds as the magma rises. When it finally reaches the surface, all that trapped gas expands explosively. The magma does not flow. It shatters into fragments that are blasted into the atmosphere. This is what produces volcanic explosions that can devastate entire regions. Between these extremes lies a spectrum of eruption styles. Andesitic magmas produce intermediate behavior. Magma composition can change during an eruption. Water entering the system can dramatically increase explosivity. The interaction between magma and its environment creates complexity that makes each eruption unique. The deadliest volcanic hazard is often not lava but pyroclastic flows. These are avalanches of superheated gas and volcanic debris that race down the slopes of a volcano at speeds exceeding 100 miles per hour. Temperatures can reach 800 degrees Celsius. Nothing survives in their path. Pyroclastic flows killed nearly 30,000 people during the 1902 eruption of Mount Pelee on the Caribbean island of Martinique. The city of Saint-Pierre was completely destroyed in minutes. Only 2 people in the city survived. One was a prisoner in a basement cell. The other was a shoemaker who happened to be at the edge of town. Volcanic ash presents another danger. During explosive eruptions, fine particles of pulverized rock can be thrown miles into the atmosphere. This ash is not soft like ash from a fire. It is essentially tiny shards of glass. Inhaled, it damages lungs. Accumulated on rooftops, it can cause buildings to collapse under its weight. Fallen into water supplies, it poisons communities. Carried by winds, it can affect areas hundreds of miles from the eruption. Lahars add water to the equation. When volcanic material mixes with water from melted glaciers, crater lakes, or heavy rainfall, it creates a mud flow of incredible destructive power. Lahars can travel tens of miles down river valleys at speeds of 40 miles per hour or more. They bury everything in their path under feet of concrete like debris. In 1985, the eruption of Nevado del Ruiz in Colombia triggered lahars that traveled 50 miles down a river valley and buried the town of Armero. More than 23,000 people died in a single night. Most were killed not by the eruption itself, but by the mud flows that reached them while they slept. Volcanic gases can kill silently. Carbon dioxide is heavier than air and can accumulate in low-lying areas near volcanoes. In 1986, Lake Nyos in Cameroon released a massive cloud of carbon dioxide that flowed downhill and suffocated more than 1,700 people and thousands of livestock in nearby villages. Tsunamis represent yet another volcanic hazard. When eruptions or volcanic flank collapses displace large volumes of water, the resulting waves can devastate coastal communities far from the volcano itself. The 1883 eruption of Krakatoa in Indonesia generated tsunamis that killed more than 36,000 people along the coasts of Java and Sumatra. Wave heights exceeded 100 feet in some locations. This brings us to one of the most terrifying possibilities: volcanic flank collapse. Large volcanic islands are not stable structures. They are essentially giant piles of loose rock built up by successive eruptions over thousands of years. The slopes are steep. The material is fractured and weak. Water percolates through the rock, weakening it further, and the whole structure sits on oceanic crust that is itself in motion. Under the right conditions, a section of a volcanic island can catastrophically collapse into the sea. The volumes involved can be enormous, tens to hundreds of cubic kilometers of rock sliding into the ocean in a matter of minutes. The geological record preserves evidence of such collapses throughout the world's volcanic islands. Hawaii shows massive debris fields on the seafloor extending for hundreds of miles from the islands. The Canary Islands bear scars from ancient collapses: Cape Verde, the Azores, Reunion, Mauritius. Wherever large volcanic islands exist, evidence of flank collapses appears in the geological record. These collapses generate tsunamis of almost unimaginable scale. Models suggest that waves exceeding 300 meters in height could impact coastlines near the collapse site. Even at distances of thousands of miles, waves could still reach heights capable of devastating coastal cities. The question is how these collapses occur. Do they happen suddenly, as a single catastrophic event, or gradually, as a series of smaller failures that add up over time? The distinction matters enormously for hazard assessment. Evidence from the Cape Verde Islands suggests that at least some collapses are sudden and catastrophic. About 73,000 years ago, the volcanic island of Fogo experienced a massive flank collapse. Researchers have found tsunami deposits on nearby Santiago Island at elevations exceeding 270 meters above sea level. This is among the highest tsunami run-up ever documented in the geological record. Similar evidence exists from Tenerife in the Canary Islands. About 170,000 years ago, a massive flank collapse generated tsunamis that deposited marine debris more than 100 meters above sea level on the island's coast. These are not theoretical possibilities. They are documented events that have occurred in the recent geological past. They will occur again. The only questions are where and when. Could Axial Seamount experience a flank collapse? The short answer is probably not, in any scenario we need to worry about. Axial is a different type of volcano than the large oceanic shield volcanoes that produce the most dangerous collapses. It is built on oceanic crust at a spreading ridge rather than on an isolated volcanic edifice. Its slopes are gentler, its structure is more stable. However, scientists have noted that if Axial's caldera were to experience complete collapse, rather than the relatively small subsidence that accompanies normal eruptions, a flank failure could theoretically occur. The likelihood is considered very low, but very low is not zero. More importantly, the same Juan de Fuca Ridge system that hosts Axial Seamount also produces the earthquakes associated with the Cascadia subduction zone. A major subduction zone earthquake could trigger submarine landslides along the continental slope. Those landslides could generate tsunamis affecting the Pacific Northwest coast. The Cascadia subduction zone itself is capable of generating tsunamis directly. When the megathrust fault ruptures, the seafloor displaces vertically. Water is pushed up or down. Waves radiate outward. The 1700 earthquake generated tsunamis that reached Japan 10 hours later. The next Cascadia earthquake will generate tsunamis that reach the Oregon coast in 15 to 30 minutes. This is the broader context that makes Axial Seamount significant beyond its own eruptions. The volcano sits within a complex tectonic system where multiple hazards interconnect. Understanding Axial helps scientists understand the entire system, and understanding the system is essential for preparing communities that face real risk from earthquakes, tsunamis, and volcanic activity. The anatomy of catastrophe includes many components: explosive eruptions, pyroclastic flows, ashfall, lahars, toxic gases, tsunamis, flank collapses. Each mechanism has its own physics, its own warning signs, its own potential for destruction. Most volcanic eruptions do not produce catastrophe. Most are small events that affect limited areas. Most give warning signs that allow populations to evacuate. Most end without significant loss of life. But history shows what happens when circumstances combine to produce something worse. Mount Pelly in 1902, Nevado del Ruiz in 1985, Krakatoa in 1883, Mount Unzen in 1792. These are not ancient history. They are events within living memory or documented in historical records. And the geological record shows that far worse is possible. Eruptions on scales that dwarf anything observed in human history, events capable of changing global climate, events capable of threatening human civilization itself, Axial. Seamount will not produce such an event. Its eruptions are too small, too deep, and too isolated to threaten populated areas directly. But the principles at work beneath Axial are the same principles that govern all volcanoes everywhere. Understanding those principles matters. The breathing mountain beneath the Pacific is part of a larger story, a story about a planet that remains geologically active, a story about forces that operate on timescales and with powers that exceed human comprehension, a story about risk that we cannot eliminate, only understand and prepare for. In the next chapter, we will explore what happens when volcanic catastrophes reach their most extreme scale. We will examine supervolcanoes and the evidence that massive eruptions have shaped human evolution. we will confront the possibility that volcanic events on a scale not seen in recorded history could occur again. The history of life on Earth is punctuated by volcanic catastrophes, mass extinctions, population bottlenecks, climate disruptions lasting years or decades. These are not hypothetical scenarios, they are documented events that have occurred repeatedly throughout geological time. Understanding that history is essential for understanding our own vulnerability. We live on a planet that has killed most of the species that have ever existed. The forces that produced those extinctions are still at work. They are merely dormant, not gone. The volcano does not distinguish between species. It does not spare civilizations. It operates according to physical laws that care nothing for human hopes or fears. Understanding those laws is how we protect ourselves, not by preventing eruptions, which is impossible, but by understanding what they can do and preparing accordingly. The anatomy of catastrophe is written in rock and ash across the planet. Learning to read that record may be the most important thing volcanologists can teach us. The breathing mountain continues its slow rise. The countdown continues, and somewhere in the depths of geological time, other mountains are preparing lessons we have not yet learned. Chapter 5. When the Earth swallows itself. There is a lake in Indonesia that should not exist. Lake Toba stretches roughly 100 kilometers long and 30 kilometers wide across the northern part of Sumatra. It is the largest volcanic lake on Earth. Crystal waters fill a depression so vast it can be seen from space. Tourists visit its shores, communities fish its waters. Life continues as if nothing remarkable ever happened here. But something remarkable did happen here. 74,000 years ago, this peaceful lake was the site of the largest volcanic eruption in the past 2 million years. An event so catastrophic that some scientists believe it nearly ended the human species. The Toba supervolcano erupted with a violence that defies ordinary comprehension. Estimates suggest the eruption expelled somewhere between 705,000 cubic kilometers of material into the atmosphere. For comparison, the 1815 eruption of Mount Tambora, which caused the year without a summer and killed tens of thousands of people, ejected roughly 150 cubic kilometers. The 1980 Mount St. Helens eruption ejected less than 3 cubic kilometers. Toba was not merely large, it was in a category essentially by itself. The eruption began deep in the earth, where magma had been accumulating for hundreds of thousands of years. A massive chamber filled with molten rock containing dissolved gases at tremendous pressure. When the chamber finally breached the surface, the result was an explosion that scattered ash across South Asia and beyond. Ash from Toba has been found in sediment cores throughout the Indian Ocean. It has been identified in soil layers across India, reaching depths of several meters in some locations. It appears in ice cores from Greenland, marking the event with a sulfate spike visible 74,000 years later. The eruption column likely reached 40 kilometers or more into the stratosphere, injecting sulfur dioxide that spread across the entire planet. The climate effects were severe. Models suggest global average temperatures may have dropped 3 to 5 degrees Celsius in the years following the eruption. A volcanic winter descended on the planet. Sunlight dimmed behind veils of sulfuric acid aerosols. Growing seasons shortened. Ecosystems already stressed by the cooling already underway during that glacial period faced additional pressure. In South Asia, nearest to the eruption, conditions would have been apocalyptic. Ash blanketed everything. Forests that had covered central India were stripped bare. Carbon isotopes in soil samples show the landscape shifted from forest to grassland in the aftermath. Animals that depended on forest habitat vanished or migrated. The regional ecosystem was fundamentally transformed. For the humans alive at that time, Toba posed an existential threat. Our ancestors had been anatomically modern for perhaps 100,000 years, but were still restricted to Africa and parts of the Middle East and South Asia. Their populations were small, their technology was limited to stone tools, they had no writing, no agriculture, no large-scale social organization. This is where the Toba catastrophe theory emerges. First proposed in the late 1990s, the theory suggested that the eruption caused such severe environmental disruption that human populations collapsed to dangerously low levels, perhaps as few as 3,000 to 10,000 breeding individuals worldwide, a genetic bottleneck that left its mark on human DNA. The evidence for this bottleneck comes from genetics rather than archaeology. Modern humans show surprisingly little genetic diversity compared to other great apes. Chimpanzee populations contain more genetic variation than all 8 billion humans combined. This suggests that our ancestors passed through a severe population reduction at some point in the past, eliminating most genetic variation and leaving all of us descended from a relatively small surviving group. The timing of this bottleneck appeared to coincide roughly with the Toba eruption. The volcanic winter seemed like a plausible mechanism. The narrative was compelling. Humanity nearly went extinct from a volcanic catastrophe, and the survivors rebuilt the species from a tiny remnant population. The theory sparked intense debate that continues to this day. Critics point out that the genetic evidence for a bottleneck does not require a volcanic cause. Population reductions could result from many factors including disease, climate change unrelated to volcanism, or simply the dynamics of small populations living at the margins of their range. The timing of the bottleneck in genetic data is also uncertain, with estimates ranging from 50,000 to 100,000 years ago depending on the methodology used. Archaeological evidence has complicated the picture further. Sites in India show stone tools both above and below the Toba ash layer that appear remarkably similar, suggesting that local populations survived the eruption and continued their way of life without dramatic disruption. Sites in South Africa show no evidence of population collapse around 74,000 years ago. If Toba nearly destroyed humanity, the archaeological record does not consistently show it. More recent climate modelling has also tempered the catastrophe narrative. While Toba certainly caused cooling, newer simulations suggest the effects may have been more regionally variable than originally thought. Parts of the southern hemisphere may have experienced little to no cooling. Some areas may have actually become more favourable for human habitation due to changed rainfall patterns. The current scientific consensus is nuanced. Toba was undoubtedly an enormous eruption with significant climate effects. It likely caused hardship for human populations, particularly those living closest to the eruption in South Asia. But it probably did not bring humanity to the brink of extinction. The genetic bottleneck observed in human DNA may have other causes, including the out-of-Africa migration that reduced diversity in non-African populations through founder effects. Yet even the revised view acknowledges something profound. A volcanic eruption on the scale of Toba is capable of affecting global climate for years. It can devastate regional ecosystems. It can make life significantly harder for human populations across wide areas. And events on this scale have happened repeatedly throughout Earth's history. Supervolcanoes are not unique curiosities. They are recurring features of Earth's geological activity. Yellowstone in Wyoming has produced 3 super eruptions in the past 2 million years. The Long Valley caldera in California marks the site of a massive eruption 760,000 years ago. The Taupo volcanic zone in New Zealand has produced multiple super eruptions, including one only 26,000 years ago. These systems are not dormant in any comfortable sense. They continue to show activity. Yellowstone experiences thousands of earthquakes per year. Ground deformation is continuously measured. Hydrothermal features shift and change. The magma system beneath the caldera remains hot and potentially capable of producing future eruptions. No super eruption has occurred in recorded human history. The largest eruptions we have witnessed directly are orders of magnitude smaller than the events preserved in the geological record. This creates a dangerous gap between human experience and geological reality. We know what a volcanic explosivity index 7 eruption looks like. Tambora showed us. We have written records and scientific understanding of its effects. We know it killed, directly through pyroclastic flows and ashfall. We know it caused climate disruption that led to famine and disease worldwide. We know the year without a summer affected agriculture from North America to China. But we have never witnessed a volcanic explosivity index 8 event. The last such eruption occurred 26,000 years ago at Taupo in New Zealand. Whatever human populations existed in the region at that time left no written records. We can only extrapolate from smaller events and geological deposits what such an eruption would mean for modern civilization. The extrapolation is sobering. A super eruption today would likely kill millions of people in the immediate vicinity through pyroclastic flows, ashfall, and collapse. Depending on location, entire major cities could be destroyed. Infrastructure across a large region would be annihilated. Evacuation at the scale required might be logistically impossible, even with advance warning. The ashfall would extend for thousands of miles downwind. Airports would close, highways would become impassable, buildings would collapse under the weight of accumulated ash, water supplies would be contaminated, agriculture would fail across wide areas, the climate effects would be global, temperatures would drop for years, growing seasons would shorten, crop failures would cascade across continents. Food supplies already stretched thin by population growth and climate change would face unprecedented strain. Famine on a scale not seen in modern history could result. The economic disruption would be staggering. Supply chains dependent on regions affected by ashfall would collapse. Global trade would be severely impacted. Financial markets would face uncertainty that current models cannot adequately address. The cost would be measured in trillions of dollars and millions of lives. This is not speculation. This is extrapolation from events that have actually occurred. The geological record shows that super eruptions happen. They happen on timescales of tens to hundreds of thousands of years. They will happen again. The only uncertainty is when. Current monitoring cannot predict when the next super eruption will occur. The timescales involved are too long for pattern recognition. The systems are too complex for physics-based forecasting at present. We might have decades of warning as a volcanic system showed increasing activity, or we might have years, or months. The uncertainty is profound. Axial Seamount is not a supervolcano. Its eruptions are tiny by comparison to Toba or Yellowstone. But studying Axial teaches us about volcanic processes that operate at all scales. Understanding how magma accumulates, how pressure builds, how failure occurs, these insights apply whether we are talking about a small submarine volcano or a continent-spanning caldera. Every observation at Axial is a data point that helps refine our understanding of how volcanoes work. Every successful or unsuccessful prediction tests hypotheses about forecasting. Every eruption observed in detail adds to the knowledge base that might someday help us prepare for something much larger. The breathing mountain beneath the Pacific is not going to threaten civilization, but it is teaching us lessons that might matter when a more dangerous volcano shows signs of awakening. That is the broader significance of the research being conducted at Axial. Not the immediate hazard, but the long-term understanding. Humanity has survived volcanic catastrophes before. Our ancestors endured Toba, whether it nearly destroyed them or merely made life harder for a generation. We have the cognitive capacity to understand volcanic hazards in ways no previous generation could. We have technology to monitor and model volcanic systems. We have global communication networks to share warnings and coordinate responses. But we have never faced a super eruption with our current population of 8 billion people, our globally interconnected economy, and our agriculture systems operating at the edge of capacity. The resilience that served our ancestors may not translate directly to modern civilization. The lesson of Toba is not that we nearly went extinct and survived. The lesson is that the Earth is capable of producing events far beyond anything in recorded human history. Events that can change global climate, events that can transform regional ecosystems, events that can test human populations in ways we cannot fully anticipate. Axial Seamount will erupt soon. It will provide valuable scientific data, and it will remind us, if only briefly, that we live on a planet that remains geologically active, a planet where fire still rises from the depths, a planet where the next catastrophe is not a question of if but when. The countdown continues, the breathing mountain continues building pressure, and somewhere beneath our feet, forces are at work that dwarf anything in human experience. Understanding those forces is not optional. It is essential for the long-term survival of our species on this beautiful and dangerous planet we call home. Full stop. Chapter 5 is now complete. I am awaiting your confirmation to continue with chapters 6 through 10. Chapter 6. The Cascade Effect. We like to think of geological events as isolated occurrences. An earthquake here, a volcanic eruption there. Separate incidents that happen and then end, allowing life to return to normal. But the Earth does not operate in isolation. Systems connect. Forces interact. One event can trigger another in cascades that multiply destruction far beyond what any single phenomenon could produce. This is the cascade effect, and understanding it is essential for grasping the true risk posed by geological hazards in regions like the Pacific Northwest. Start with the basic geography. The Cascadia subduction zone runs for roughly 1,000 kilometers from northern Vancouver Island to Cape Mendocino in northern California. Along this boundary, the Juan de Fuca plate is being pushed beneath the North American plate at a rate of about 4 centimeters per year. The plates do not slide smoothly past each other. They lock together, building stress over centuries until the accumulated strain exceeds the friction holding them in place. Then they slip, catastrophically. The last time the Cascadia subduction zone ruptured was January 26, 1700. The earthquake was massive. Magnitude estimates range from 8.7 to 9.2. The fault broke along nearly its entire length. The shaking lasted for minutes, and then came the tsunami. We know the date and approximate time with remarkable precision because of records kept half a world away. Japanese documents describe an orphan tsunami, waves that arrived without the warning of a local earthquake, working backward from the arrival time in Japan and modelling how long it would take waves to cross. The Pacific scientists determined that the earthquake occurred around 9 in the evening Pacific time. The indigenous peoples of the Pacific Northwest preserved oral histories of that night. Stories speak of shaking so violent that people could not stand, of the ground opening, of villages swept away by great waves, of a world transformed in moments from familiar to terrifying. 325 years have passed since that earthquake. The plates have continued moving. Stress has continued accumulating. The average interval between major Cascadia earthquakes is roughly 500 years, but intervals have ranged from 200 to 900 years. We are well within the window when the next great earthquake could occur. Scientists estimate a 37% probability of a magnitude 8 or greater earthquake on the Cascadia subduction zone within the next 50 years. A 10 to 15% probability of a magnitude 9 event that ruptures the entire fault. These are not negligible numbers. They represent genuine risk that affects millions of people. But the earthquake itself is only the beginning of the cascade. When the fault ruptures, the seafloor will move. In some areas it will drop. In others it will rise. This vertical displacement generates the tsunami. Water pushed up by rising seafloor radiates outward as waves. Water rushing in to fill areas of subsidence adds to the disturbance. The result is a series of waves that can travel across entire ocean basins. For the coast of Oregon and Washington, the tsunami will arrive within 15 to 30 minutes of the earthquake. There will be little time to evacuate. Communities that have not prepared, that have not identified high ground, that have not practiced evacuation routes, will face waves potentially reaching heights of 20 to 30 meters in some locations. The shaking and the tsunami will damage infrastructure across the region. Bridges will fail, roads will crack and buckle, power lines will come down, water and sewer systems will break, communication networks will be disrupted. The modern systems that communities depend on for daily survival will cease to function over a wide area. This is where the cascade accelerates. Without functioning infrastructure, emergency response becomes extraordinarily difficult. Hospitals may be damaged or inaccessible. First responders may be victims themselves. Supply chains that normally deliver food, fuel, and medicine will be broken. Communities will be isolated, cut off from outside help by damaged roads and fallen bridges. The coast will be particularly vulnerable. Many communities sit in low-lying areas accessible only by a few roads that cross rivers and bays on bridges. When those bridges fail, the communities become islands. Supplies cannot get in. Injured people cannot get out. Days or weeks may pass before help arrives. Meanwhile, the earthquake will have triggered secondary hazards. Landslides will block roads and bury buildings. Liquefaction will cause structures to sink into suddenly unstable ground. Fires will break out from broken gas lines and damaged electrical systems. Without water pressure for firefighting, blazes may burn unchecked. And then there are the volcanoes. The Cascade Range contains a chain of volcanoes stretching from British Columbia to Northern California. Mount Baker, Glacier Peak, Mount Rainier, Mount St. Helens, Mount Adams, Mount Hood, Mount Jefferson, Three Sisters, Newberry, Crater Lake, Mount Shasta, Lassen Peak. These are not extinct relics. They are active volcanoes capable of erupting with devastating effect. The relationship between large earthquakes and volcanic activity is complex and not fully understood. Some evidence suggests that major earthquakes can trigger volcanic eruptions by destabilizing magma systems or opening pathways for magma to reach the surface. Other evidence suggests the relationship is weak or non-existent. What we know is that the same tectonic forces driving the Cascadia subduction zone also drive the volcanism of the Cascade Range. The Juan de Fuca plate descending beneath North America releases water into the overlying mantle, lowering the melting point of rock and generating the magma that feeds Cascade volcanoes. The systems are connected at the deepest level. A major Cascadia earthquake might not trigger an immediate volcanic eruption, but it could destabilize systems that were already building toward eruption. It could accelerate timelines. It could push a volcano that might have remained quiet for decades toward activity within years or months. Mount Rainier represents a particular concern. Rising more than 14,000 feet above the Puget Sound lowland, Rainier is the most glaciated peak in the contiguous United States. Its summit and flanks are covered with more than 30 square miles of ice. The volcano is also extensively altered by hydrothermal activity, with rock weakened by acidic fluids that have been circulating through the edifice for thousands of years. This combination creates conditions for lahars, volcanic mud flows that can travel tens of miles down river valleys at speeds of 40 miles per hour or more. Lahars from Mount Rainier have reached Puget Sound multiple times in the past several thousand years. The valleys leading from the mountain now contain communities housing more than 100,000 people. A lahar triggered by volcanic activity, or potentially by earthquake-induced collapse, could devastate these communities with little warning. Current monitoring and alert systems might provide 30 minutes to an hour of warning at best. For communities directly in the path, that may not be enough time to evacuate. The cascade effect means that we cannot think about hazards in isolation. An earthquake triggers a tsunami. The tsunami damages infrastructure. Damaged infrastructure hampers response. Secondary hazards compound the disaster. Volcanic activity might follow weeks or months or years later, striking communities still struggling to recover. This is the reality of living in the Pacific Northwest. Multiple hazards interconnect in ways that multiply their effects. Preparing for one hazard without considering the others leaves communities vulnerable to cascading failure. Axial Seamount fits into this picture in specific ways. Its eruptions do not directly threaten coastal communities. The volcano sits too far offshore and too deep underwater to produce immediate hazards for populated areas. But Axial is part of the same tectonic system that drives Cascadia earthquakes and cascade volcanism. Studying Axial provides insight into the behavior of the Juan de Fuca plate. Every earthquake recorded at Axial adds to our understanding of how stress accumulates and releases in this region. Every eruption observed reveals how magma moves through oceanic crust that is ultimately connected to the subduction zone. The research conducted at Axial also advances general volcano science in ways that benefit monitoring of dangerous volcanoes worldwide. Methods developed to forecast eruptions at this submarine laboratory can be tested and refined before being applied to volcanoes where lives are at stake. There is another connection worth noting. The Ocean Observatories Initiative that monitors Axial Seamount also includes instruments on the continental slope that track activity related to the Cascadia subduction zone. Seismometers and pressure sensors provide data on slow slip events, episodic tremor, and other phenomena that may be related to stress accumulation on the megathrust fault. If funding cuts force the shutdown of the cabled array, we lose not only the volcano observatory at Axial, but also monitoring infrastructure relevant to earthquake hazards. The cascade effect works in reverse as well. Decisions made about scientific funding cascade through the research enterprise, affecting capabilities that may seem unrelated but are deeply connected. The Pacific Northwest is a beautiful region. Forests reaching to the ocean, mountains rising against the sky, rivers thick with salmon, cities vibrant with life and creativity. It is easy to forget that this landscape was shaped by catastrophe and will be shaped by catastrophe again. The 1700 earthquake left ghost forests along the coast, drowned trees killed when the land suddenly dropped and salt water flooded the roots. Mount Mazama exploded 7,000 years ago, creating Crater Lake and blanketing the region with ash. Mount St. Helens reminded us in 1980 that volcanic violence is not confined to the distant past. These events will happen again. Not might, will. The tectonic forces driving them continue operating regardless of human activity or awareness. The only questions are when and how well prepared we will be. The cascade effect means that preparation must be comprehensive, not just earthquake readiness, not just tsunami evacuation routes, not just volcano monitoring. All of these together, coordinated and sustained, backed by communities that understand the risks and have practiced responses. Axial Seamount will erupt in 2026 or thereabouts. It will provide scientific data, it will test forecasting methods, and it will remind us, briefly, that we live in a geologically active region where the next catastrophe is always approaching. The countdown at Axial continues. The countdown on the Cascadia subduction zone continues. The countdown for the next cascade eruption continues. Multiple clocks, multiple timelines, multiple hazards, all connected through the deep structure of the Earth beneath our feet. Understanding those connections is the first step towards survival. The cascade effect multiplies destruction. But understanding and preparation can break the cascade, reducing impacts at each stage and preventing secondary hazards from compounding primary ones. That is the work that matters. That is why research at places like Axial Seamount matters. That is why monitoring and preparation and public education matter. The Earth does not care about our schedules or our convenience, but we can care about understanding it, and understanding is the foundation of resilience. The cascade awaits. The question is whether we will be ready when it begins. Chapter 7. Volcanic Winter. April 1815. The Indonesian island of Sumbawa. A mountain that had slumbered for centuries decided to wake up. Mount Tambora had been rumbling for days. Small explosions. Columns of smoke. The local population knew something was happening but could not know what was coming. No one alive had ever witnessed what Tambora was about to do. On the evening of April 10th, the volcano exploded with a force that remains the largest volcanic eruption in recorded human history. The sound was heard nearly 2,000 kilometers away. People in distant cities thought they were hearing cannon fire and sent troops to investigate non-existent battles. The eruption column rose more than 40 kilometers into the stratosphere, punching through the boundary between the lower and upper atmosphere. Within hours, pyroclastic flows had swept across the peninsula, killing everyone in their path. Entire villages vanished. The population of Sumbawa, estimated at around 12,000 before the eruption, was nearly annihilated. Ash fell across the Indonesian archipelago, collapsing roofs and poisoning water supplies. Tsunamis struck nearby coastlines. The immediate death toll reached at least 10,000, possibly many more. But the killing was only beginning. The eruption injected enormous quantities of sulfur dioxide into the stratosphere. There, the gas combined with water vapor to form tiny droplets of sulfuric acid. These aerosols spread across the planet, carried by upper atmosphere winds. Within weeks, a veil of sulfuric acid haze encircled the Earth. The aerosols reflected incoming sunlight back into space before it could warm the surface. Global temperatures began to drop. The effect was not immediately obvious. Weather varies from day to day and month to month. But as the month passed, a pattern emerged. The summer of 1816 was not arriving. In New England, frost persisted into June. Snow fell in Albany, New York, and other northern cities during what should have been warm summer months. Crops that had been planted in spring froze in the fields. Farmers watched helplessly as their harvests failed before their eyes. Across the Atlantic, Europe suffered even more severely. The continent was still recovering from decades of warfare that had ended just the year before with Napoleon's final defeat. Food supplies were already strained. When the crops failed across wide areas, famine followed. In Ireland, cold temperatures and relentless rain destroyed the potato and grain harvests. The poor, already living at the margins of survival, began to starve. Disease spread through weakened populations. Typhus epidemics swept through communities. The death toll mounted through 1816 and into 1817. Germany experienced bread riots as prices soared beyond what ordinary people could afford. Switzerland saw waves of beggars flooding the cities from rural areas where nothing would grow. France faced unrest that tested a government barely established after years of revolution and war. In China, the effects were equally devastating. The Yunnan province, dependent on rice cultivation, experienced 3 consecutive years of failed harvests. Cold weather and flooding destroyed crops that communities depended on for survival. Famine killed tens of thousands. The crisis was so severe that it inspired poetry lamenting the suffering, reviving an ancient literary form dedicated to recording injustice and tragedy. The Yunnan famine had another consequence that would echo through the following century. Desperate farmers, searching for any crop that could survive the disrupted climate, turned to growing opium poppies. The region became a major production centre for the drug trade that would later fuel conflicts and addiction across Asia. In India, the disruption of the monsoon system caused widespread drought. The weakening of normal rainfall patterns affected agriculture across the subcontinent, and in the disrupted conditions, a new strain of cholera emerged in the Bengal region. This mutated pathogen would spread globally over the following years, causing a pandemic that killed millions. 1816 became known as the year without a summer. It was not that summer disappeared entirely. Temperatures dropped only a few degrees on average, but those few degrees made an enormous difference. Growing seasons shortened below the minimum needed for crops to mature. Frost struck at times when it should have been impossible. The margin between survival and starvation proved terrifyingly narrow. The cultural effects of the year without a summer linger to this day. Mary Shelley, vacationing in Switzerland during the cold, gloomy summer of 1816, found herself trapped indoors by incessant rain. To pass the time, she and her companions challenged each other to write ghost stories. The result was Frankenstein, one of the foundational works of science fiction, born from a volcanic winter that its author did not understand. The painter J.M.W. Turner captured the strange atmospheric effects of the post-Tambora years in canvases showing vivid red and orange sunsets. The aerosols in the upper atmosphere scattered light in unusual ways, producing spectacular sky colours that artists across Europe documented. These paintings remain a visual record of volcanic climate disruption. Tambora was a volcanic explosivity index 7 event, large by any measure, devastating in its effects, but not the largest category of eruption the Earth can produce. The scale goes up to 8, and the difference between 7 and 8 is not incremental. The volcanic explosivity index is logarithmic. Each step up represents roughly a tenfold increase in the volume of material ejected. A V8 eruption expels 10 times more material than Tambora did. The effects of such an eruption on global climate would be correspondingly more severe. Instead of temperatures dropping a degree or two, they might drop 5 or 10 degrees. Instead of one summer without warmth, there might be a decade of disrupted climate. Instead of regional famines and epidemics, there might be global catastrophe on a scale that threatens civilization itself. We have never witnessed a VEI-8 eruption. The last one occurred about 26,000 years ago at Taupo in New Zealand. Human civilization did not exist in any recognizable form. No written records document the effects. We can only extrapolate from smaller events and geological evidence. The extrapolation is frightening. Modern civilization depends on global supply chains that deliver food from producing regions to consuming populations. Many countries import a substantial fraction of their food supply. A disruption that lasted years rather than months would overwhelm existing reserves. Rationing might buy time, but eventually stocks would be exhausted. Agriculture itself might become impossible across wide areas. Growing seasons shortened by several degrees of cooling would prevent staple crops from maturing. Alternative crops adapted to cooler conditions might not be available in sufficient quantity to plant. The knowledge and infrastructure needed to pivot agricultural systems might not exist or might not function quickly enough. Energy systems would face unprecedented strain. Heating demand would increase just as supply chains for fuel were disrupted. Electrical grids already operating near capacity would struggle with increased load. The social and economic disruption would make maintaining complex infrastructure extraordinarily difficult. Financial systems built on assumptions of continuous growth would face conditions for which they were not designed. Insurance companies would face claims exceeding their reserves. Banks would confront loan defaults cascading through the economy. The monetary system itself might come under strain as governments struggle to respond to simultaneous crises across multiple sectors. This is not speculation about unlikely scenarios. This is extrapolation from events that have actually occurred. Tambora happened. The year without a summer happened. The famines and epidemics and social disruption happened. And Tambora was small compared to what the Earth is capable of producing. The volcanic systems that could produce V8 eruptions exist today. Yellowstone, Taupo, Toba, the Indonesian arc that produced both Tambora and Toba. These are not extinct. They are dormant. The distinction matters. Current monitoring cannot tell us when the next super eruption will occur. The timescales are too long for pattern recognition. The precursors are not well enough understood for reliable forecasting. We might have decades of warning, we might have years, we might have months. The uncertainty is profound. What we can do is understand the mechanisms, study how volcanic aerosols affect climate, model the agricultural and social consequences of extended cooling, develop contingency plans for scenarios that seem unlikely but would be catastrophic if they occurred. Axial Seamount contributes to this understanding in indirect but important ways. Every observation of volcanic processes adds to the knowledge base. Every refinement of eruption forecasting methods potentially applies to larger and more dangerous systems. The submarine laboratory off Oregon is part of a global effort to understand volcanic hazards that could affect everyone on Earth. The immediate concern with Axial is not climate effects. Its eruptions are too small and too deep to inject significant material into the atmosphere. But the principles at work beneath Axial are the same principles at work beneath every volcano. Understanding those principles matters for predicting and preparing for events that could be genuinely catastrophic. The year without a summer was a warning from history, a demonstration that volcanic eruptions can affect global climate with consequences measured in lives lost and societies disrupted. That warning came from an eruption smaller than the largest events in the geological record. We live in a brief window of volcanic quiescence. No VEI 7 or 8 eruption has occurred during the era of modern civilization. Our agricultural systems, our supply chains, our financial institutions, our governments have never been tested against volcanic climate disruption at the scale that Earth can produce. That quiescence will not last forever. The volcanic systems capable of producing catastrophic eruptions remain active. The forces driving them continue operating. Eventually, inevitably, one of them will erupt on a scale that reminds humanity just how powerful this planet can be. Understanding that power is not cause for despair, it is motivation for preparation. The more we know about volcanic climate effects, the better we can prepare for them. The more we study volcanic systems, the better chance we have of forecasting eruptions in time to take protective action. Axial Seamount is one small piece of this larger effort, but every piece matters. Every observation contributes. Every refinement of understanding brings us closer to being ready for whatever the Earth decides to throw at us next. The volcano that changed the summer of 1816 is still there. Mount Tambora remains an active stratovolcano capable of future eruptions. It erupted again in 1880 on a much smaller scale. It shows continuing signs of activity today. The systems that drive volcanic eruptions do not care about human civilization or human timescales. They operate according to physics and chemistry that have been at work for billions of years. They will continue operating long after we're gone. Our choice is whether to understand those systems and prepare accordingly, or to remain ignorant and vulnerable. The year without a summer showed what volcanic climate disruption can do. The geological record shows that much worse is possible. The countdown continues at Axial Seamount. Other countdowns continue at volcanic systems around the world. The breathing mountains do not rest. They only wait. And somewhere in the future that none of us can see, another Tambora is building toward the moment when it will remind the world what volcanoes can do. Chapter 8. When humanity almost ended. 74,000 years ago, our ancestors faced something they could not understand. A darkness that lasted for years. A cold that killed the plants and animals they depended on. A world transformed from familiar to hostile in ways that no living memory could explain. The Toba supervolcano had erupted. On the island of Sumatra, where Lake Toba sits today as the largest volcanic lake on Earth, a magma chamber that had been building for hundreds of thousands of years finally broke through to the surface. The eruption was approximately 100 times larger than any volcanic event in recorded human history. Perhaps 2,800 cubic kilometers of material blasted into the atmosphere and across the surrounding region. The immediate effects were devastating across Southeast Asia. Pyroclastic flows swept outward from the eruption center. Ash fell in depths measured in meters across the Indonesian archipelago. India, more than 2,000 kilometers away, received ash deposits that can still be identified in the geological record today. The eruption column reached the stratosphere and dispersed material around the entire planet. And then came the volcanic winter. Sulfur dioxide from the eruption combined with water vapor to create a global veil of sulfuric acid aerosols. Sunlight dimmed. temperatures dropped. Models suggest the cooling may have reached 3 to 5 degrees Celsius globally, with more severe effects in specific regions. The volcanic winter may have lasted 6 to 10 years. The broader climate disruption possibly persisted for a century or more. For the humans alive at that time, this was an existential crisis. Anatomically, modern humans had evolved roughly 130,000 years earlier in Africa. Small groups had begun migrating out of the continent, establishing populations in the Middle East and South Asia. But these populations were small and vulnerable. Their technology was limited to stone tools. They had no agriculture, no stored food reserves, no ability to relocate quickly across large distances. The TOBA, catastrophe theory, first proposed in the late 1990s, suggested that this eruption nearly drove our species to extinction. The evidence came from genetics rather than archaeology. Modern humans display remarkably little genetic diversity compared to other great apes. A population of a few dozen chimpanzees contains more genetic variation than all 8 billion humans alive today. This lack of diversity suggests that at some point in our past, the human population passed through a severe bottleneck, a period when only a small number of individuals survived and reproduced, becoming the ancestors of everyone alive today. Genetic analysis pointed to a bottleneck occurring somewhere between 50,000 and 100,000 years ago. The timing seemed to coincide with TOBA. The mechanism, volcanic winter causing widespread starvation and death, seemed plausible. The narrative was compelling. Humanity was reduced to perhaps 3,000 to 10,000 breeding individuals. We survived by the narrowest of margins. Every person alive today is descended from that tiny remnant population that somehow endured the darkness. This story has become deeply embedded in popular understanding of human origins. It appears in documentaries, textbooks, and countless articles about the fragility of our species. The idea that we nearly went extinct has a certain dark appeal. It makes our existence seem both precious and precarious. But science does not stand still. And the evidence accumulated over the past 2 decades has complicated the TOBA catastrophe theory significantly. Archaeological sites in India have revealed stone tools both above and below the TOBA ash layer that appear virtually identical. If the eruption had devastated local populations, we would expect to see significant changes in tool technology as survivors rebuilt or new populations moved in. Instead, the continuity suggests that at least some populations survived the eruption without major disruption. Sites in South Africa, far from the eruption centre, show no evidence of population collapse around 74,000 years ago. Human occupation continued without obvious interruption. The archaeological record does not support the idea of near extinction across all human populations. Climate modelling has also evolved. More sophisticated simulations suggest that the cooling from TOBA, while significant, may have been more regionally variable than originally thought. Parts of the southern hemisphere may have experienced little to no temperature change. Some regions may have actually benefited from altered rainfall patterns. The global catastrophe narrative has given way to a more nuanced picture of regional impacts. The genetic evidence itself has been reinterpreted. The human population bottleneck may have resulted from factors other than TOBA. The migration out of Africa necessarily involved small founder populations that carried only a fraction of African genetic diversity. This founder effect could explain the reduced diversity in non-African populations without requiring a near-extinction event. African populations show a different pattern, with bottlenecks occurring at different times and potentially for different reasons. Climate fluctuations during Ice Age cycles may have repeatedly stressed human populations. The bottleneck we observe in the genetic data may reflect the cumulative effect of multiple challenging periods rather than a single catastrophic event. The current scientific consensus, if such a thing exists for contested questions, is nuanced. TOBA was undoubtedly an enormous eruption with significant climate effects. It likely caused hardship for human populations, particularly in South Asia nearest the eruption. Some local populations may have been devastated or driven to extinction, but the evidence does not support the idea that humanity as a whole came close to extinction. Multiple populations survived in multiple locations. The genetic bottleneck observed in modern humans probably reflects a combination of factors including migration dynamics, regional climate challenges, and perhaps volcanic effects, but not a single near-extinction event. This revised view does not diminish the significance of Toba. An eruption of that magnitude remains one of the most powerful geological events in recent Earth history. Understanding its effects advances our knowledge of how supervolcanoes impact climate, ecosystems, and human populations. What the revised view does is complicate the simple narrative. Reality is messier than stories. The evidence resists the dramatic interpretation even when that interpretation is more compelling. Science requires following the data wherever it leads, even when it leads to conclusions that are less emotionally satisfying. There is still much we do not know about what happened during and after the Toba eruption. The archaeological record for this period is sparse across most of the world. Genetic analysis continues to refine our understanding of population histories. New evidence could shift the consensus in either direction. What we can say with confidence is this: large volcanic eruptions can affect human population significantly. Climate disruption lasting years can stress societies dependent on agriculture and natural resources. The effects are likely to be uneven, with some regions and populations more severely impacted than others. We can also say that humanity has survived multiple periods of severe climate stress throughout our evolutionary history: ice ages, droughts, volcanic winters. Our ancestors endured conditions that would test modern civilization severely. They survived because they were adaptable, mobile, and able to exploit diverse resources. Modern civilization is different. We have vastly larger populations dependent on complex systems that require continuous functioning to provide food, water, energy, and shelter. We have less ability to relocate when conditions become unfavorable. We have less knowledge of how to survive without the technological infrastructure we have built. A super eruption today would not encounter small bands of hunter-gatherers who could relocate to more favorable regions and wait out the crisis. It would encounter 8 billion people dependent on agricultural systems that require specific climate conditions, supply chains that span continents, and infrastructure that cannot be quickly rebuilt if disrupted. The lessons of Toba are not primarily about near extinction. They are about vulnerability. They are about understanding that the Earth is capable of producing events far beyond anything in recorded human history. They are about recognizing that our current period of relative volcanic quiescence is temporary, not permanent. Axial Seamount will not produce another Toba. Its eruptions are tiny by comparison, and the volcano itself is not capable of super-eruption scale events. But studying Axial contributes to understanding volcanic systems generally. Every observation of how magma moves and accumulates, how pressure builds and releases, how eruptions initiate and progress, adds to the knowledge base that might someday help us anticipate and prepare for something much larger. The Breathing Mountain off Oregon is a window into processes that operate beneath every volcano on Earth. The same physics governs Axial and Yellowstone, though the scales differ enormously. Understanding the small scale improves our ability to understand the large scale. Toba reminds us that catastrophic volcanic events are not hypothetical. They have happened. They have affected human populations. They have shaped the trajectory of our species in ways we are still working to understand. The question is not whether another Toba will occur. The geological record shows that super eruptions happen roughly every 100,000 years on average. The question is when and whether we will be better prepared than our ancestors were. 74,000 years ago, humans survived Toba through resilience and adaptability. They did not understand what was happening. They could not predict or prepare. They simply endured generation after generation until conditions improved. We have something our ancestors lacked. We have knowledge. We understand volcanic systems in ways that would have seemed like magic to people living through the Toba winter. We can monitor volcanic activity. We can model climate effects. We can prepare contingency plans. Whether we choose to use that knowledge is up to us. The Earth will continue operating according to its own imperatives regardless of human choices. The magma chambers will continue filling. The pressure will continue building. The countdowns will continue in volcanic systems around the world. The story of Toba is not about near extinction. It is about what happens when volcanic forces exceed anything in human experience. It is about the gap between what we have witnessed and what is possible. It is about the importance of understanding that gap and preparing accordingly. Our ancestors survived Toba. The question is whether modern civilization could survive its equivalent. The answer depends on choices we make now while the mountains are quiet and we have time to prepare. The countdown continues. The breathing mountains wait. And somewhere in the depths of geological time, the next catastrophe is already building. Chapter 9: The Cascadia Connection. On the night of January 26, 1700, the world along the Pacific Northwest coast ended. The Cowichan people on Vancouver Island felt the shaking first. So violent they could not stand, so prolonged it made them sick. Houses collapsed around them, the ground opened in places, and then came the water. On the west coast of Vancouver Island, the Pachena Bay people were sleeping in their winter village when the wave arrived. The tsunami swept away everything, every house, every canoe, every person. No survivors. The entire community erased in moments. 300 miles to the south, along the Oregon coast, other communities experienced their own versions of catastrophe. Oral histories passed down through generations speak of a night when the ocean withdrew and then returned with devastating force. Villages that had existed for generations vanished. The landscape that survivors recognized was transformed beyond recognition. This was the last Great Cascadia earthquake, magnitude 8.7 to 9.2, a rupture that extended nearly 1,000 kilometers along the subduction zone fault. The largest earthquake to strike this region in at least several hundred years. We know the precise date because of records kept in Japan. Around midnight on January 27th, 1699 by the Japanese calendar, a tsunami arrived at coastal communities on Honshu. The waves came without warning. No earthquake had been felt. Japanese scholars noted the anomaly, an orphan tsunami with no apparent source. Nearly 3 centuries later, scientists pieced together the evidence. The timing of the Japanese tsunami matched what would be expected if waves had traveled across the Pacific from the coast of North America. Tree ring studies of ghost forests along the Washington and Oregon coasts dated the death of coastal trees to the winter of 1699 to 1700, consistent with sudden subsidence during an earthquake. Indigenous oral histories provided details of the shaking and flooding that written records could not. The pieces fit together to reveal an event of staggering power, and they raised a question that haunts the Pacific Northwest to this day. When will it happen again? The Cascadia subduction zone does not rupture on a predictable schedule. The geological record shows at least 19 major earthquakes over the past 10,000 years. The intervals between events range from roughly 200 to 900 years. The average is somewhere around 500 years. 325 years have passed since 1700. We are within the window when the next great earthquake could occur. Not will occur at a specific time, could occur at any time. The scientific estimate puts the probability of a magnitude 8 or greater earthquake at about 37% over the next 50 years. The probability of a full margin rupture producing a magnitude 9 event is 10 to 15% over the same period. These numbers deserve careful consideration. A 37% probability over 50 years is not a prediction that an earthquake will happen. It is an acknowledgement that the risk is substantial and ongoing. Every year that passes without an earthquake does not make the next year less likely to have one. The fault continues accumulating stress regardless of how long it has been since the last release. The connection between Axial Seamount and the Cascadia subduction zone operates at multiple levels. Most fundamentally, both are driven by the same tectonic forces. The Juan de Fuca plate is being created at the spreading ridge where Axial sits and destroyed at the subduction zone where it dives beneath North America. The plate's motion connects these two regions in a continuous system. What happens at one end affects what happens at the other, though the connections are complex and not fully understood. Axial Seamount provides a window into the behavior of the Juan de Fuca plate. Every earthquake recorded at Axial adds to our understanding of how stress accumulates and releases in oceanic crust. Every eruption reveals how magma moves through the plate. This knowledge informs models of how the plate behaves as it approaches and enters the subduction zone. The Ocean Observatories Initiative that monitors Axial also includes instruments on the continental slope that track activity related to the Cascadia subduction zone. Seismometers detect earthquakes along the margin. Pressure sensors measure deformation that might indicate stress changes on the megathrust fault. The integrated network provides data on the entire system, from spreading ridge to subduction zone. One phenomenon of particular interest is episodic tremor and slip. Every 13 to 16 months, a slow slip event occurs along the deeper portions of the Cascadia subduction zone. The plates move past each other over a period of weeks in a motion too slow to generate felt earthquakes, but detectable by precise GPS measurements and sensitive seismometers. These slow slip events release some of the stress accumulating on the fault, but they occur at depths below the locked zone where major earthquakes originate. Their relationship to the likelihood of megathrust earthquakes is still being studied. Some researchers suggest that slow slip events might increase stress on the locked zone above, potentially bringing it closer to failure. Others suggest the opposite, that stress release at depth might delay rupture of the shallower locked zone. The uncertainty reflects how much we still do not know about how subduction zones work. Cascadia is particularly challenging because it produces very few of the small and moderate earthquakes that help scientists understand stress conditions at other subduction zones. The fault appears to be almost completely locked, storing stress without releasing it through background seismicity. This silence is not comforting. It may indicate that when Cascadia does rupture, it will release centuries of accumulated stress in a single catastrophic event. The 1700 earthquake may be representative of what to expect, or it may have been relatively small compared to what Cascadia can produce. The implications for communities in the Pacific Northwest are profound. When the next great Cascadia earthquake occurs, shaking will be felt from British Columbia to Northern California. The intensity will vary depending on distance from the rupture, local geology, and building construction. But major cities including Vancouver, Seattle, Portland, and potentially Sacramento will experience shaking strong enough to damage or destroy structures not built to withstand it. Many buildings in the region are not adequately designed for the shaking expected from a magnitude 9 earthquake. Unreinforced masonry structures are particularly vulnerable. Bridges, overpasses, and other infrastructure may fail. Lifeline systems, including water, power, and communications, may be disrupted for extended periods. The tsunami will compound the disaster along the coast. Communities have limited time to evacuate to high ground. Those who cannot reach safety in 15 to 30 minutes may not survive. The waves may reach heights of 20 to 30 meters in some locations, surging inland and destroying everything in their path. The economic impact will be measured in hundreds of billions of dollars. The human impact will be measured in lives lost and communities destroyed. The recovery will take years, possibly decades. This is not speculation. This is extrapolation from the 1700 event, and from similar earthquakes at other subduction zones. The 2011 Tohoku earthquake in Japan killed nearly 20,000 people and caused damage exceeding $200 billion. Cascadia is capable of producing an earthquake of similar or greater magnitude. The connection to Axial Seamount is indirect but real. Studying Axial advances our understanding of the tectonic system that drives Cascadia earthquakes. The monitoring infrastructure at Axial contributes to observations of the broader region. The scientific community that studies submarine volcanism overlaps with the community that studies subduction zone hazards. More broadly, Axial reminds us that the Pacific Northwest is geologically active. The same forces that will produce the next axial eruption are connected to the forces that will produce the next Cascadia earthquake. These are not separate hazards to be considered independently. They are manifestations of a single underlying reality. The Earth beneath the Pacific Northwest is in motion. Preparing for one hazard without considering the others creates vulnerability to cascading failures. A community that has earthquake preparedness plans but no tsunami evacuation routes is not fully prepared. A region that focuses on volcanic monitoring but neglects seismic hazards is missing part of the picture. The countdown at Axial Seamount is measured in months to years. The countdown on the Cascadia subduction zone is measured in years to centuries. Both countdowns are running. Both will eventually reach zero. The question is not whether these events will occur, but whether we will be ready when they do. Axial will erupt soon. The eruption will provide scientific data and test, forecasting methods. It will cause no direct harm to human populations, but it will serve as a reminder that the systems driving volcanic and seismic hazards in the Pacific Northwest remain active. That reminder may be valuable. Complacency is the enemy of preparedness. It is easy to forget about hazards that operate on timescales longer than human memory. It is easy to prioritize immediate concerns over risks that may not materialize for decades. Axial Seamount erupting in 2026 will not cause the Cascadia earthquake, but it will demonstrate that geological forces in the region are ongoing. It will generate attention and perhaps motivate action. It will remind millions of people that they live in a dynamic landscape shaped by forces far more powerful than anything human. The indigenous peoples of the Pacific Northwest understood this. Their oral histories preserved knowledge of the 1700 earthquake across generations. They knew that the land could shake, that the ocean could rise, that catastrophe could come without warning. Modern science has confirmed their knowledge and extended it. We understand the mechanisms behind earthquakes and tsunamis in ways they could not. We can estimate probabilities and model consequences. We have tools for preparation that they lacked. What we sometimes lack is the wisdom to use those tools. The knowledge exists. The question is whether we will act on it. The Cascadia subduction zone will rupture again. Axial Seamount will erupt again. The volcanic arc of the Cascades will produce eruptions again. These are not possibilities, but certainties. The only uncertainties are timing and consequence. The breathing mountain beneath the Pacific is connected to forces that have shaped the Pacific Northwest for millions of years, and will continue shaping it for millions more. Understanding those connections is essential for living safely in a region where geological hazards are woven into the fabric of the landscape. The countdown continues at Axial, on Cascadia, at volcanoes throughout the Cascade Range. Multiple timelines, multiple hazards, all connected through the deep structure of the Earth. The question is not whether disaster will come. The question is whether we'll be ready when it does. Chapter 10. What happens next? The instruments never sleep. 300 miles off the Oregon coast beneath a mile of dark water, sensors continue their patient work. Seismometers record every tremor. Pressure recorders track the slow rise of the seafloor as magma accumulates below. Temperature probes monitor hydrothermal vents. Data streams continuously through fiber optic cables to shore, where computers compile it and scientists analyze it. Axial Seamount is breathing, swelling, building toward eruption. The current forecast points to mid to late 2026. The scientists who made that forecast are the first to acknowledge its uncertainty. They have been wrong before. The volcano does not follow their schedules. It operates according to physical laws that we understand imperfectly and cannot control at all. But the direction is clear, magma is accumulating, pressure is increasing, the inflation that precedes eruption continues. Eventually, inevitably, the volcano will let go. When it does, here is what we expect to happen. Earthquake activity will increase dramatically in the days or hours before the eruption. Swarms of small earthquakes will signal that rock is fracturing as magma forces its way toward the surface. The seismometers of the cabled array will record thousands of events, their frequency and intensity climbing toward a peak. Then, the eruption will begin. Lava will break through the seafloor, most likely along fissures in the caldera or along the rift zones extending to the northeast and southwest. The molten rock will meet cold seawater, instantly chilling to form pillow basalts and sheet flows that spread across the terrain. The caldera floor will drop as magma drains from the chamber below. In previous eruptions, the subsidence has exceeded 2 meters. Instruments positioned on the caldera floor may be buried or destroyed. The landscape that cameras have been watching will be transformed in hours. Hydrothermal activity will intensify. Fresh magma near the surface will heat groundwater to extreme temperatures. Existing vents may become more vigorous. New vents may open. The chemistry of vent fluids may change as different minerals dissolve into superheated water. The eruption will continue for days, possibly weeks, until the driving pressure is exhausted. Then activity will taper off. The volcano will begin inflating again as fresh magma enters the chamber from below. The cycle will reset for another decade or two until the next eruption. For scientists, this will be an extraordinary opportunity. No submarine volcano has ever been monitored so comprehensively during an eruption. The data generated will inform volcanic science for decades. Every detail observed will refine our understanding of how eruptions work. The forecasting methods being tested will face their ultimate examination. Did the predictions prove accurate? Where did they succeed, and where did they fail? What can be learned that improves future forecasts? The physics-based models being developed by international teams will be evaluated against reality. If they outperform simple pattern recognition, they may revolutionize how we approach eruption forecasting worldwide. If they fail, the failures will teach us something about the limits of current approaches. For the broader public, the eruption will be a media event. Headlines will announce the volcanic activity off the Oregon coast. Some stories will emphasize the eruption itself. Others will use it as a hook to discuss broader volcanic and seismic hazards in the Pacific Northwest. Social media will spread information and misinformation in equal measure. There will be questions about safety. Is the coast threatened? Could there be a tsunami? Will the eruption trigger something larger? Scientists will patiently explain that Axial poses no direct threat to populated areas. The volcano is too far offshore and too deep underwater to generate hazards that reach the coast. But the questions will persist because they reflect genuine anxiety about living in a geologically active region. The same forces that produce axial eruptions produce the earthquakes and volcanic hazards that do threaten coastal communities. The eruption will serve as a reminder that those forces are ongoing. This reminder may be the eruption's most significant impact on human society. It is easy to forget about hazards that operate on timescales longer than human memory. The last great Cascadia earthquake was more than 3 centuries ago. The last major Cascade eruption was Mount St. Helens in 1980. Within living memory but fading, the risks feel abstract, theoretical, something to worry about someday but not today. Axial erupting in 2026 will make the risks feel more immediate. Here is a volcano actually erupting right now off our coast. Here are scientists who predicted it months in advance using the same methods they apply to other volcanoes. Here is evidence that the Earth beneath the Pacific Northwest remains active. That sense of immediacy may translate into action. Emergency preparedness drills, infrastructure improvements, public education campaigns, political will to fund monitoring and research. The eruption itself will cause no harm, but attention generated by the eruption might help prevent harm from future events that do threaten populated areas. Or the attention may fade quickly, replaced by the next news cycle and the endless demands of daily life. History is full of warnings that went unheeded, disasters that were predictable but not prevented because complacency returned faster than memory. The choice belongs to the communities and governments that will experience the eruption as news rather than as direct reality. Axial Seamount cannot make that choice for them. It can only demonstrate, one more time, that the geological forces shaping the Pacific Northwest continue operating whether humans pay attention or not. Beyond the immediate eruption, larger questions remain. The Cascadia subduction zone continues accumulating stress. Every year that passes brings the next great earthquake closer without telling us when it will arrive. The probability estimates remain what they were: 37% for a magnitude 8 or greater earthquake in the next 50 years, 10 to 15% for a magnitude 9. These numbers may not change significantly based on anything that happens at Axial, but awareness of the numbers may change. Understanding of what they mean may deepen. Motivation to prepare may increase. The Cascade volcanoes continue their own countdowns. Mount Rainier has not had a major eruption in roughly 1,000 years, but it shows ongoing hydrothermal activity that signals an active magmatic system. Mount Hood last erupted around 1781. Mount Shasta, Mount Baker, Glacier Peak all retain the potential for eruptions that could affect populated areas. Monitoring these volcanoes is essential for providing warning when activity increases. The methods developed at Axial contribute to monitoring capabilities everywhere. The scientists who study submarine volcanism share knowledge and techniques with those who study volcanic hazards on land. The funding that supports this research remains uncertain. Budget proposals have suggested dramatic cuts to ocean observing systems, including the infrastructure that monitors Axial. The Trump administration proposed an 80% reduction to programs that fund the cabled array. As of late 2025, the array has secured funding through mid-2026. Beyond that, nothing is guaranteed. If funding is cut, the most comprehensive volcano observatory ever built on the seafloor could go dark, just as the volcano it monitors approaches eruption. The scientific community would lose access to data that cannot be collected any other way. Methods that could save lives at other volcanoes would go untested. This would be a tragedy for science and potentially for public safety. But it would be a choice, not an inevitability. Societies choose what to fund and what to cut. Those choices reflect priorities and values. The question is whether understanding geological hazards ranks high enough among those priorities to receive sustained support. Axial Seamount does not care about human choices or human priorities. It will erupt whether we are watching or not. The cabled array allows us to learn from the eruption. Without it, we learn much less. The countdown continues regardless. In the darkness beneath the Pacific, magma rises through fractures in ancient rock. Pressure builds in a chamber that has been filling for nearly a decade. The seafloor continues its slow rise, centimetre by centimetre, toward a threshold that must eventually be exceeded. The scientists watching from shore refine their forecasts and wait. They know the eruption is coming. They do not know exactly when. They have done everything possible to be ready, and they acknowledge the limits of what is possible. This is the nature of volcano science in 2026, better than it has ever been, still fundamentally uncertain, improving steadily through hard work and honest evaluation. Facing challenges that no technology can fully overcome, Axial Seamount will erupt. The eruption will advance our understanding of volcanic processes. That understanding will contribute to protecting communities from volcanic hazards worldwide. The breathing mountain will teach us something new, as it has taught us something new with every eruption we have observed, and then the cycle will begin again. Inflation, building pressure, waiting for the next threshold to be exceeded. The volcano does not rest. It only prepares. This is the story of Axial Seamount, a window into the deep earth, a laboratory for understanding volcanic processes, a reminder that we live on a planet that remains geologically active, a countdown that will continue until it reaches zero and then begin again. The eruption is coming, 2026 or thereabouts. The scientists are watching, the instruments are recording, the data is streaming to shore at the speed of light, and somewhere in the darkness beneath a mile of cold Pacific water, fire is rising toward the surface. Patient, inevitable, indifferent to human hopes and fears, the breathing mountain is about to exhale. If you enjoyed this deep investigation into Axial Seamount and the volcanic hazards of the Pacific Northwest, please like this video and subscribe to the channel. Your support makes these detailed explorations possible. Tell me in the comments which geological phenomenon should we investigate next. The supervolcano beneath Yellowstone, the earthquake swarms along the San Andreas Fault, the volcanic islands of Hawaii where new land is being created right now, or perhaps something unexpected, a geological mystery with a story waiting to be told. These places are not just scientific curiosities, they are chapters in the ongoing story of our planet, a planet that has been reshaping itself for 4.5 billion years, a planet that will continue reshaping itself long after we're gone, a planet where understanding the forces at work is essential for survival. Every volcano has its story, every earthquake zone has its history, every geological hazard carries lessons for those willing to learn them. The breathing mountain off Oregon is telling its story right now. The question is whether we are listening. Thank you for watching. I will see you in the next investigation.